There is a reason Challenger exploded that almost no one talks about. The people who built the rocket knew the joint was broken. They had known since 1977. There were memos, and on the night before the launch, the engineers got on a phone call and begged NASA not to fly. But NASA flew anyway. This is what actually happened on the Space Shuttle Challenger disaster. The Space Shuttle had two enormous solid-fuel rocket boosters strapped to the sides of its fuel tank. These were the largest solid-fuel rockets ever built in the United States. Once they were lit, they could not be turned off. They burned until their fuel was gone, and that took about 2 minutes. Each booster was 14 stories tall, too big to ship in one piece. So they were built in segments, 4 fuel sections per rocket, and the segments were bolted together at the launch site. The places where 2 segments met were called field joints. There were 3 of them on each booster. Inside each field joint sat 2 rubber rings. They were called O-rings. They were about 1/4 of an inch thick, and each one was wrapped around a circle 12 feet in diameter, about 37 feet of rubber per ring. They were the only thing keeping the burning gas inside the rocket. If those rings failed, flame would punch through the side of the booster like a blowtorch through tin foil. That is the part to hold on to. The contractor who built the boosters was a company called Morton Thiokol in Utah. They had won the contract on November 20, 1973. NASA selection officials wrote in their final report that Thiokol's cost advantages were substantial and consistent. They wrote that any selection other than Thiokol would give rise to an additional cost of appreciable size. The contract was $800 million. Thiokol borrowed the joint design from an older rocket, the Air Force's Titan III, one of the most reliable solid rockets ever produced. The Titan used a single rubber seal, with the segment insulation pressed tightly enough that the rubber rarely had to do real work. Thiokol's design used 2 rings instead of 1, and added a small port on the side of the case that engineers could pressurize to test the seals before flight. The selection officials wrote that this was an innovative design feature that increased reliability. Then they started testing, and the design did not behave the way it was supposed to. In 1977, Thiokol ran what were called hydroburst tests. They filled a booster casing with water and pressurized it to 1.5 times the actual operating pressure. Then they measured what happened to the joint. The expectation was that under pressure, the metal joint would squeeze tighter. Instead, the engineers watched the joint bulge outward. The wall of the rocket bowed away from itself because the joint was 3 times thicker than the wall, and the wall was the part that flexed. The gap between the 2 metal pieces opened up. The phenomenon was called joint rotation. Thiokol's supervisor of structures, Arnold Thompson, would later testify before the Rogers Commission. He said they discovered the joint was opening rather than closing, contrary to their original analysis. He said it was opening up to about 52 thousandths of an inch at the primary O-ring. The problem was simple. The rubber rings now had to stretch in the wrong direction, in milliseconds, while the metal under them was peeling open. The Thiokol engineers went to the company that made the rubber, the Parker Seal Company, and asked for advice. According to Feynman, the Parker Seal Company told Thiokol that O-rings were not meant to be used that way. They could give no advice. A NASA engineer at Marshall Space Flight Center named Leon Ray had been watching the test data. In October 1977, he wrote a report titled Solid Rocket Motor Joint Leakage Study. He called the existing design unacceptable. He recommended a redesign of the tang and a tighter clevis tolerance. In January 1978, the chief of Marshall's Solid Motor Branch, John Q. Miller, signed a memo to his superior. The memo said there was no valid reason for not designing to accepted standards. It said improvements were mandatory to prevent hot gas leaks and resulting catastrophic failure. A year later, when no response had come back, Miller signed another memo. This one called Thiokol's position regarding design adequacy of the joint completely unacceptable. It said the way the rubber was being asked to function violated industry and government O-ring application practices. The Rogers Commission later determined that Leon Ray had actually written both memos. Miller had signed them and concurred. Both Marshall engineers were on record. According to the Commission, Thiokol never received copies of either Miller memo. The booster design passed its first certification review in March 1979 anyway. Marshall management concluded the safety factors were adequate. Then came the flights. And on the flights, the joint started to burn. On the second shuttle mission, in November 1981, an O-ring showed in-flight erosion for the first time. It was the right booster's aft field joint. The damage went 53 thousandths of an inch deep. According to the Commission report, this anomaly was not even reported to the Marshall Problem Assessment System at the time. It got no tracking number. In December 1982, a quiet bureaucratic change happened. NASA reclassified the booster joint from Criticality 1R to Criticality 1. The R stood for redundant. Removing it meant the agency had officially admitted, on paper, that the second O-ring could no longer be counted on as a backup. Criticality 1 was defined as a system whose single failure causes loss of mission, vehicle, and crew. 3 months later, in March 1983, the Associate Administrator for Spaceflight, Michael Weeks, signed a waiver. The waiver let the shuttle continue to fly with the Criticality 1 joint. Weeks later told the Commission that everyone in the program at the time felt the booster was probably one of the least worrisome things they had. Then the cold weather pattern began to surface. On Flight 41B, in February 1984, inspectors found erosion in a field joint and a nozzle joint at the same time. The Rogers Commission report shows the launch temperature was 57 degrees Fahrenheit. On Flight 41C, 2 months later, 3 more O-ring anomalies at 63 degrees. On 41D in August, more damage at 70. On Flight 51C in January 1985, the temperature at launch was 53 degrees. The boosters came back with 5 separate O-ring anomalies, including, for the first time, heat effect on a secondary seal. The backup had been engaged. Around the same time, NASA had quietly raised the pressure of a routine pre-flight test on the joints. The test pushed air through the small port between the 2 O-rings to confirm they were seated. The original pressure was 50 pounds per square inch. By 1984, it had been raised to 200. The higher pressure made it easier to verify the seal. It also, as Marshall engineer John Q. Miller pointed out in another memo, blew tiny holes through the asbestos-filled putty that was supposed to protect the rings from the flame. The numbers tell a clean story. Of the first 9 shuttle flights, when the leak test was at 50 or 100 pounds, only 1 field joint anomaly was found. Once the test pressure went to 200, more than half the missions came back with field joint erosion or blow-by. On the nozzle joints, the rate climbed from 12% to 56% to 88% as the test pressure went up. So the agency's own pre-flight verification, the one designed to confirm the seal was good, was making the seal worse. In April 1985, on Mission 51B, it got worse still. A nozzle primary O-ring had been damaged and had failed to seat at all. The secondary seal was eroded too. For the first time, the backup had been needed, and the backup had also been chewed up. Lawrence Malloy, the Marshall manager in charge of the solid rocket booster project, formally placed a launch constraint on the program. From that point forward, every shuttle flight required a written waiver to fly with the known O-ring problem. Malloy signed 6 waivers in a row. The 7th would have been Challenger. In August 1985, Thiokol set up an internal task force to fix the joint. According to the Rogers Commission, company engineers told investigators the task force ran into red tape and a lack of cooperation. A memo from one of the engineers said the result of a leak at any joint would be catastrophic. That word, catastrophic, was already on paper in the company's own files months before the launch. Now, let's talk about the schedule, because the schedule is what kept all of this moving. The space shuttle had been sold to the country as the future of access to space. Reusable, routine, cheap. NASA had retired its expendable rockets in favor of the shuttle. Original plans imagined a flight a week by 1985 that had been walked back to 24 flights a year by 1990. The Rogers Commission later concluded that even the modified goal of 2 flights a month was overambitious. The system, the Commission wrote, had been stretched to the limit just to support the 9 flights of 1985. Spare parts were running out. Astronaut training time was being cut. Late changes to payloads were disrupting flight planning. The agency was running on a culture that refused to admit it could not keep up. Challenger's mission, Flight 51L, had originally been scheduled for July 1985. By the time the crew was assigned, it had slipped to November, then late January. The mission carried 2 satellites, including a small science platform meant to study Halley's Comet before the comet disappeared into the sun's glare on February 9. With every delay, the science window narrowed. It also carried Krista McAuliffe, a high school social studies teacher from New Hampshire, the first private citizen ever assigned to a shuttle flight. She had been preparing 2 lessons since September. She planned to teach them from orbit. Standing on the runway at the Kennedy Space Center after she arrived in Florida, she said she didn't think any teacher had ever been more ready to have 2 lessons in her life. She said she just hoped everybody would tune in to watch the teacher teaching from space. It was the last public statement she ever made. The first launch attempt was scrubbed because of weather concerns at an emergency landing strip in Senegal. The second attempt, on January 27, ran into a comedy of small failures that would be funny in any other story. A hatch handle that wouldn't lock, a drill brought to fix it whose batteries were dead. A delay long enough that crosswinds at the landing strip went out of limits. The crew, who had been strapped into the shuttle for more than 5 hours, climbed out and went back to their quarters. Launch was rescheduled for the morning of January 28. That night, the temperature in central Florida dropped toward freezing, and the engineers at Morton Thiokol got nervous. They got on a phone call. It started in the evening on January 27. On the line were Thiokol engineers in Utah, NASA managers at Marshall in Alabama, and the launch team at Kennedy in Florida. The subject was simple. The forecast for launch morning called for the coldest temperatures any shuttle had ever launched in. The previous record was 53 degrees, the launch where they had first seen the cold weather damage to the secondary seal. The forecast for January 28 was 26 degrees overnight, with launch temperatures barely above freezing. The Thiokol engineers, led by a man named Roger Boisjoli, presented their data. They showed the correlation between cold and O-ring damage. They had charts. They had photographs of past damage. Their recommendation was unanimous. Do not launch below 53 degrees Fahrenheit. The NASA managers at Marshall pushed back. They argued the engineers did not have enough data to support the temperature limit. They asked, in the words of Thiokol engineer Alan MacDonald, who later disclosed the story to the Rogers Commission when Thiokol wanted them to launch. Next April, the engineers held their ground. Then Thiokol management asked for a recess to caucus offline. The phone line went silent on Florida and Alabama's end. In Utah, the company's senior managers told their engineers, in a phrase that has been quoted ever since, to take off their engineering hats and put on their management hats. They overruled their own engineers. When the phone call resumed, Thiokol's official position had reversed. Launch was approved. Roger Boisjoli later testified to the Rogers Commission about that meeting. He said one of his colleagues summed it up best. This was a meeting where the determination was to launch, and it was up to the engineers to prove beyond a shadow of a doubt that it was not safe to do so. He said this was in total reverse to what the position usually was in a flight readiness review. He said they were being put in a position to prove they should not launch, rather than being put in the position to prove they had enough data for launch. That reversal is the contributing cause of the disaster. NASA had spent decades operating on a principle that you do not fly unless you can prove the vehicle is safe. On the night of January 27, that principle was inverted. The engineers were now being asked to prove the vehicle was unsafe. And the threshold for proof was set so high that no amount of data was going to clear it. Word of the debate was never passed up the chain to senior NASA management. The launch was approved. The teleconference ended. The engineers in Utah went home knowing what they knew. That night, ice built up on the launch pad. At 1 a.m. on January 28, technicians began loading 500,000 gallons of super-cold liquid hydrogen and liquid oxygen into the external tank. Wind chills on the pad reached 10 degrees below zero. Infrared scans of the right-side booster showed temperatures at the base of the rocket well below freezing. The coldest spot, on the suspect aft field joint, was estimated at 28 degrees Fahrenheit. The crew arrived at the pad shortly after sunrise. Krista McAuliffe wore gloves to keep out the cold. The technicians who had greeted her with mortarboards on the previous attempt presented her with a shiny red apple. The cabin temperature inside the shuttle was 61 degrees. The astronauts strapped in. Now let's come back to the joint. Because the joint is where this whole story has been heading since 1973. It was a record 36 degrees when Challenger took off. The two rubber rings inside the suspect joint were stiff. Cold rubber does not spring back into shape the way warm rubber does. According to the Rogers Commission, a compressed rubber ring at 75 degrees Fahrenheit is about 5 times more responsive than the same ring at 30 degrees. The rings in Challenger's right booster were, in the language of the Commission report, probably not following the opening of the gap at the time of ignition. There was something else. Challenger had been on the pad for a month. During that month, Central Florida had received about 7 inches of rainfall. The Rogers Commission noted there was a possibility that water had made it into the joint. The night before launch, that water would have frozen. So at the moment the boosters lit, somewhere between the 2 to 170 degree and 3 to 110 degree position around the right-hand aft field joint, something failed. The rubber did not move, or the ice prevented a seal, or the metal flexed open a fraction wider than the cold ring could follow. Hot gas, at thousands of degrees, found a path past the seal. At 0.678 seconds after ignition, less than 3/4 of a second into the flight, photographs from a tracking camera show the first puff of black smoke spurting from the suspect joint. The smoke came from the side of the booster facing the external fuel tank. The smoke was black, which meant the grease, the joint insulation, and the rubber were burning. For the next 2 seconds, 8 more puffs of smoke escaped the joint. They came in a rhythm of about 3 per second, which roughly matched the natural structural frequency of the rocket as it shook off the pad. Each puff darker than the one before. Then, at 2.733 seconds after liftoff, the smoke stopped. The smoke stopped because the gap had resealed itself. As the rubber and the insulation and the grease burned, the byproducts, mostly aluminum oxide, deposited a fragile crust over the breach. The Rogers Commission later concluded this was the most likely scenario. The joint had failed at ignition, and then, just as the leak should have grown, combustion debris plugged it. That plug was the only reason Challenger got off the pad. For the next 56 seconds, the shuttle climbed normally. The crew was talking on the intercom. Mike Smith, the pilot, said it was a little hard to see out his window. He said it looked like they had a lot of wind. Wind shear during this flight was, in fact, more extreme than on any of the previous 24 shuttle missions. According to the Rogers Commission report, the steering system was more active than on any prior flight, fighting to keep the vehicle on its trajectory. That fight is what knocked the plug loose. At 58.788 seconds, image-enhanced film shows the first flicker of flame on the side of the right-side booster in the same spot the smoke had come from. 1 frame later, the flame was visible without enhancement. By 59.2 seconds, it had grown into what investigators called a continuous, well-defined plume. At about the same moment, telemetry recorded a pressure difference between the 2 boosters. The right one was lower. It was leaking. The flame was hot enough and large enough that the airflow around the booster bent it backward and to the side, directly onto the surface of the giant external fuel tank. That tank held liquid hydrogen in its lower section and liquid oxygen on top. The hydrogen tank was made of aluminum. The flame began to eat through it. At 64.660 seconds, the shape of the flame changed abruptly. It started mixing with leaking hydrogen. The breach had reached the tank. In the cockpit, the crew had no warning of this. The shuttle did not have any sensors that could tell its pilots a booster joint was burning through. Even if they had known, there was nothing they could have done. The boosters could not be shut off. Separating from the tank while the boosters were still firing would have driven the orbiter into the bottom of the tank. At 68 seconds, Mission Control radioed up. "Challenger, go at throttle up." Commander Dick Scobie answered. "Roger. Go at throttle up." It is the last thing anyone outside the cockpit ever heard from Challenger. At 72.2 seconds, the lower strut connecting the right booster to the external tank gave way. The booster, still firing at full thrust, swung loose from its bottom mount and rotated forward on its top attachment, swinging like a door. At 73.124 seconds, the bottom of the external tank's hydrogen section blew out. The tank released a sudden surge of forward thrust as the hydrogen vented, shoving the entire upper section into the liquid oxygen tank above it. The 2 propellants met. The right booster, swinging, smashed into the intertank structure. At 73.191 seconds, a brilliant flash appeared between the orbiter and the tank. Inside the cockpit, Mike Smith said the last words ever recorded on the crew intercom. "Uh-oh." The fireball that followed was not technically an explosion. It was a sudden, massive burning of fuel released into the atmosphere. The shuttle was traveling at nearly twice the speed of sound, at about 46,000 feet, when the burn enveloped it. Aerodynamic forces did the rest. The orbiter, under loads it was never designed to take, tore apart. This is the part that gets the most wrong, in the popular memory. Most people believe Challenger exploded and the crew died instantly. The Rogers Commission found something different. The crew compartment, the pressurized cabin where the 7 astronauts sat, did not explode. It tore loose from the rest of the orbiter as a single intact unit. Photographs taken by ground tracking cameras show it emerging from the fireball, still flying upward. It continued climbing for about 25 seconds, reaching an altitude of around 65,000 feet before it began to fall. When the cabin separated from the fuselage, the crew's main oxygen supply was left behind. But each astronaut wore a sealed flight helmet connected to a small emergency air pack mounted on the back of their seat. These were called personal egress air packs. Each one held about 6 minutes of unpressurized air. They were intended for ground emergencies, in case the cabin filled with toxic fumes during a pre-launch evacuation. Of the 4 air packs eventually recovered from the wreckage, 3 had been activated. Pilot Mike Smith's was on. The activation switch on his pack was on the back of his seat, somewhere he could not have reached himself. Someone behind him, either Judy Resnick or Ellison Onizuka, had reached up and turned it on. Smith's pack showed more than 3/4 of its air had been used. The air packs did not provide pressurized air. So if the cabin lost its pressure during the breakup, the packs alone could not have kept the crew conscious. NASA's investigation could never determine whether the cabin lost pressure. The crash with the ocean obliterated the evidence. But the activation of 3 of the 4 packs strongly suggests something happened that made the crew reach for them. Astronaut Robert Crippen later told the commission he believed the cabin lost pressure. because if it had not, there would have been no reason to activate the packs at all. So, one of two things happened to the crew during those final 2 minutes and 45 seconds. Either they lost consciousness in the seconds after the breakup when the cabin depressurized and they never woke up, or they did not lose pressure and they were aware, in some form, all the way down. The cabin hit the Atlantic Ocean about 18 miles northeast of the launch pad at around 200 miles per hour on the commander's side. It was traveling fast enough that the impact subjected the crew to a force of about 200 times normal gravity. Anyone still alive at that moment was killed instantly. The forward seats were bent sharply to the right by the impact. The window glass in the cockpit was shattered, but pieces remained in their frames. The cabin disintegrated and settled on the bottom, 100 feet below. The remains of all 7 astronauts were eventually recovered. The Armed Forces Institute of Pathology was unable to determine a cause of death. Joseph Kerwin, the director of life sciences at the Johnson Space Center, conducted the official analysis. His final report concluded the cause of death could not be positively determined. He concluded the forces of orbiter breakup were probably not enough to cause death or serious injury. He concluded the crew possibly, but not certainly, lost consciousness in the seconds following the breakup due to in-flight loss of cabin pressure. The president appointed an independent commission to investigate the accident. It was chaired by William Rogers, a former Secretary of State. Its vice chairman was Neil Armstrong. Its members included the astronaut Sally Ride, the test pilot Chuck Yeager, and the physicist Richard Feynman. Feynman was the one who broke it open in public. A few days after the accident, he was at home in California, reluctant to fly to Washington. He had a standing personal rule against going anywhere near the federal government. According to his own account, his wife told him he would make a unique contribution. He accepted. He told her he was going to commit suicide for 6 months. He was briefed by engineers at the Jet Propulsion Laboratory before he ever set foot in Washington. On the second line of the notes he took during that briefing, he wrote that the O-rings showed scorching in Clevis check. According to his own account, he was told what was wrong with the shuttle on the second line of the second day. What followed, in his telling, was a study in friction. The Rogers Commission, in its first weeks, did not investigate. It held public meetings. It received briefings. It wrote talking points about how to handle the press. Feynman pushed for direct conversations with engineers. He was told to be patient. He was told the commission would proceed in an orderly manner. The break came on a phone call from one of the other commissioners, Major General Donald Kutina. Kutina told Feynman he had been working on his carburetor and had been thinking. He asked, casually, what the effect of cold was on the rubber seals. Feynman caught on immediately. The launch temperature had been near freezing. The coldest previous launch had been 53 degrees. The next morning, in a public commission meeting, Feynman asked NASA for a glass of ice water. He had bought clamps from a hardware store. He pulled a piece of the booster O-ring rubber out of a model, clamped it, and dunked it in the ice water. When he pulled it out, the rubber stayed compressed. It did not spring back. He told the room, on camera, that this material had no resilience whatsoever at that temperature. It was a kitchen table experiment. It made the front pages. What Feynman discovered when he kept investigating was that the same disease ran through the rest of the program. He visited the Marshall Space Flight Center to ask about the main engines. Without warning the engineers in the room, he asked each of them to write down, on a piece of paper, what they thought the probability of catastrophic failure was per flight, due to engine failure. He got 4 answers. 3 engineers wrote, in slightly different phrasings, about 1 in 200. The 4th answer came from a manager named Lovingood. It said the number could not be quantified. Feynman told Lovingood he thought he had weaseled. Lovingood said his actual number was 100%. Then he caught himself and said minus epsilon. Feynman asked what epsilon was. Lovingood said 1 in 100,000. Feynman wrote in his appendix to the commission report that this number was a fantasy. 1 in 100,000 meant the shuttle could fly every day for 300 years and lose only one. He wrote that the working engineers gave numbers around 1 in 100. The managers above them gave numbers 1,000 times smaller. He could not understand, he wrote, where management's fantastic faith in the machinery came from. His appendix described the agency's pattern of decision-making with a phrase that stuck. He called it a kind of Russian roulette. The shuttle flies with O-ring erosion, he wrote, and nothing happens. Then it is suggested that the risk is no longer so high for the next flights. Standards get lowered a little because they got away with it last time, he wrote. You got away with it, but it shouldn't be done over and over again like that. He also went after the use of the term safety factor. NASA had argued that because the worst observed O-ring erosion had only gone 1/3 of the way through the rubber, and laboratory tests showed a ring would still seal even with damage 3 times that deep, there was a safety factor of 3. Feynman wrote that this was not what a safety factor meant. He compared it to a bridge. A bridge designed to carry 3 times its rated load is using the safety factor for what it was built for, to absorb the unknown. A bridge carrying its rated load with cracks already in the beams is not safe. The cracks are a sign the design is failing. He wrote that the O-rings were never designed to erode. Erosion was a clue that something was wrong. Erosion was not something from which safety could be inferred. The Commission's conclusion about the immediate cause of the accident was direct. The failure was due to a faulty design, unacceptably sensitive to a number of factors. Those factors were the effects of temperature, physical dimensions, the character of materials, the effects of reusability, processing, and the reaction of the joint to dynamic loading. In plain English, the seal was bad, and everyone who needed to know it knew it. The Commission's conclusion about the contributing cause was harder. It read that the decision to launch was flawed. Those who made that decision were unaware of the recent history of problems concerning the O-rings and the joint, and were unaware of the initial written recommendation of the contractor advising against launch at temperatures below 53 degrees Fahrenheit. They were unaware of the continuing opposition of the engineers at Thiokol after their management reversed its position. The Commission wrote that if the decision-makers had known all of the facts, it is highly unlikely that they would have decided to launch on January 28, 1986. Feynman wrote his appendix on his own. He nearly had to fight to get it included. According to his account, the Commission's executive officer marked up sections of it with circles and crosses, calling them repetitive. Feynman threatened to take his name off the front of the main report unless his appendix appeared without modification. He won. The appendix appeared. It ended with a single sentence that has been quoted ever since. For a successful technology, reality must take precedence over public relations, for nature cannot be fooled. There are things we still do not know, 4 decades later. We do not know exactly when the crew of Challenger lost consciousness or whether they did at all. We do not know if water in the joint froze and contributed to the failure, or if the cold rubber alone was enough. We do not know, with certainty, the precise sequence of the seal's collapse in the first 0.6 of a second after ignition, because the 2 cameras on launch pad 39B that would have recorded the exact location of the smoke were inoperative that morning. We do not know how many other launch eve debates like the one on January 27 had happened on previous flights and were never made public because the flight had succeeded and there was nothing to investigate. The wreckage of the crew compartment is still on the floor of the Atlantic, in a place the Rogers Commission deliberately removed from its public charts. Somewhere in a facility in Utah, the redesigned booster joints, the ones built after the disaster, are still being assembled the way the Commission ordered, with more O-rings, with electric heaters wrapped around the seal area, with a redesigned tang and clevis that does not bulge open under pressure. Every joint flown since 1986 traces back to a memo that was written 8 years before the accident, by an engineer named Leon Ray, whose copies the contractor never received. The engineers who tried to stop the launch were right. They had been right for years. Nobody listened in time.